Hello everyone and welcome to another video. Today I'd like to talk a little bit about complex numbers, variables, and functions. So we're going to see that this discussion is the foundation and sort of the first step in our exploration of ordinary differential equations. So today let's keep it just general and kind of abstract from a mathematical perspective and just talk about complex numbers, complex variables, and complex functions. So maybe the easiest way to start off thinking about complex numbers is let's start thinking about normal real numbers. So I've actually got two daughters, and my older one is in elementary school, and they're just starting to talk about real numbers or the number line, right? Which is nothing fancy. I think you guys all understand that the number line is just this line that stretches out from one direction to the other direction to infinity. It's got 0 in the middle, and then you've got positive numbers moving off to the right, and then you've got negative numbers moving off to the left. Okay, so the concept with a complex number is now let's have this number not just have to live on the real line, but let's introduce another axis. Let's introduce an imaginary axis like such, which has positive imaginary values going up and negative imaginary values going down. Okay? So you might ask, what is an imaginary component? So the way we're going to denote this is, let's say you've got a complex number z. It might have a value x, which is real, but then associated with it, it also has a component y, which is imaginary. And the imaginary I'm going to denote here as I. And if you remember, the concept here is I, or sometimes j. People use different notations depending on what mathematical text you write. This is the concept of square root of minus 1. Right? So the way to think about this now is this number z, it doesn't just live on this real line, it lives in this real imaginary plane. So you might have a z sitting out here, which has now real component x and imaginary component y. Right? So you can visualize this z here as either like a point in space, or we're going to see later on that it might also be helpful to think about this as a vector. Maybe we'll draw it like that. Okay? So this is what an imaginary number is. It's just it's a coordinate or a vector in this real imaginary plane. Okay. So I'll tell you what. Let's jump over to Matlab real quick and look at how can we define imaginary numbers in Matlab.
All right, so Matlab actually natively supports complex numbers, and it uses the symbols I or j to represent them. So as you can see, I here has 0 real component and a unit imaginary component, and same thing for j. So as you can imagine, if you were to say I squared or j squared, you get -1. So this is great. So what we can do is we can now use this to define a complex number. Let's make something like, I don't know, how about my complex number? I'll make a variable, and I want this to be, how about 2 plus 3 times I? So this is all fine and dandy. If we run this script, you see that it defines your complex number as 2 plus 3i. So this is super easy to define complex numbers in Matlab. Now, while we're sitting here in Matlab, let me show you a small gotcha that you might want to worry about or just be aware about. Whatever you do, do not use I and j as loop counters. What do I mean by that? A lot of times I'm sure you're going to write yourself for loops. And if you've taken CSE classes or you've read textbooks, what is every computer scientist's favorite loop iterator? They use I, right? They say for I gets 1 to 3, right? Do something, right? Maybe I'll just print out display hello 3 times, right? So if you do this, what's the danger? Let's go ahead and execute this script. And now at the end of line 8, what we've done is, if you think about this long enough, we've blown away and overwritten MATLAB's definition of the complex variable I with this loop counter. So now at the end, if we run this again, let's put a breakpoint in. And I'll just step through this. So line 2 executes normally as expected, right? You get this complex number. But now, if we go through this loop 3 times, notice now it doesn't have a value of square root of -1. It has a value of 3 by the time we drop out of this loop. So if you came down here in line 10 and you want to do something like, how about my other complex number is 4 plus 2 times I, right? And you expect that to be a complex number. You know what? It's not going to be a complex number. In fact, let's just run this and you'll see this is going to evaluate to something completely different than maybe what you were to expect. Yep. See, this did not come out to 4 plus 2i. It came out to the real number 10. So again, just be a little careful of how you use the variables I and j within MATLAB, especially when you're dealing with complex numbers.
All right, so let's come back here to our vector representation of this complex number z. Since we've drawn it here as a vector, you might be able to say, and we can make some observations, that why don't we talk about things like what's the magnitude of this vector and what's the angle that this vector makes from the real axis. Maybe let's call this angle theta. So as you can see from geometry, this is pretty easy, that the magnitude of this complex number, let me draw it like this. This is effectively the length of this, right? And if you notice, since this is a right angle right here, you can basically use Pythagorean theorem and say that, okay, the magnitude of z, that's just the square root of the real component plus the imaginary component square rooted, right? So this gives you the length of this vector here. And the angle associated with it, right? This angle, this is now, it's just what? It's the inverse tangent of the y over x, okay? And again, here's a slight gotcha. This is not actually a very preferred way to go about this, right? This is not a 4-quadrant inverse tangent, right? Because what you like here is I'd like this angle to be able to go from 0 all the way down to negative 360, right? Because, for example, you might have another variable out here, right? And the angle in this case would be all the way around, right? That would be theta, right? Now the problem here is this, when you have just a single input argument to the inverse tangent, right? It can't tell what quadrant it came from, right? Because if you had something in the positive quadrant, like up here, that would be the same thing as if you had something in the negative quadrant, right? Because the negatives would cancel itself. So in general, this is not a good approach. I would not recommend using a single argument inverse tangent when you're computing the angle associated with, actually, heck, with any vector, right? Really, you should be using something like an a tan 2 to use MATLAB speak. Now, here's another one of these interesting places where we have to worry a little bit. A tan 2, it's actually, in general, any 4-quadrant inverse tangent, you have to go ahead and make sure you understand and read the manual of the software package that you're using. What I mean by that here is, in this case, in MATLAB's speak, let me just make myself a little table, okay? So MATLAB, in order to do a 4-quadrant inverse tangent, the function it uses is a tan 2, okay? And we have to worry about what is the first input and the second input. So let me just go ahead and make a table. Maybe let's do it like this. Okay, and maybe, sorry, we should fill up the header. So this is the software. This is the function name. And here's the first input. So the first input that you do in MATLAB is you give it the y component, right? Or the imaginary component, or the vertical component, however you want to think about it. And then the second input you give it is the x component. Now you might be saying, duh, this is no problem. But the reason I call this out is because Mathematica, other packages, okay, it's got another function which does something similar. It has the arctan function. And you know what? The way you call arctan is you give it the x component first and then the y component. So this is one of these situations where you really have to read the manual, right? I'm sure you guys have seen this RTFM. It stands for read the fine manual. How about? Let's put it that way. I'll let you guys Google this if you want. But again, just be a little bit careful when you're computing the inverse tangent. Make sure you know what is the order of the inputs to give it, right? So I tell you what, let's jump over to the computer real quick and I'll just verify that this is actually the case in these two situations.
All right, so if you just come here and you say help a tan 2, you'll see that this is the 4-quadrant inverse tangent. And look at this. The manual tells you you better give me y and then x in that order. So again, let's go ahead and make a vector give it these kind of components. So you can kind of see that this should be in the first quadrant. It's probably around 25-ish degrees, something like that. But if we want to actually compute this, let's go ahead and call a tan 2, and we give it y and then x. And this should give us theta. Okay, and maybe let's also convert this to degrees. So theta times 180 over pi should give it to us in degrees, right? Because a tan 2 is going to give it to this answer to us in radians. So if we go ahead and run this script, we see, yes, it's indeed 26.56 degrees is the angle associated with that. Now, coming over to Mathematica, let's take a look and see if that's similar. So again, in Mathematica, it's got arctan, okay? And if we go ahead and look at the help menu for this, we should see that arctan, if you zoom in, maybe this is not going to be too easy to see. Let me see if I can zoom in a little bit. You can see Mathematica wants it in the exact opposite order. It wants x and then y. So here, what we have to do is, again, we can go ahead and define x, and we can define y. But I better make sure I pass in x and then y in order to get theta out. Whoops. Come on. There we go. Okay, to get theta out. And again, let's convert theta to degrees and turn it into a number, and I'll just shift enter that, and there you go. So you see, in this case, we both get the same answer because we are careful about the ordering here. So both cases, we get 26.56 is the angle.
All right, great. So we now understand how to compute the angle associated with a complex number. And actually, before we leave this discussion, this is a great point to insert a math joke. I love math jokes. You know, have you ever seen these old school telephones? You remember when you had to dial a number in here, and sometimes if you got the wrong number, did you ever get the message, "I'm sorry, you've dialed an imaginary number. Please rotate your handset 90 degrees and then try again." You get it? Get it? Because you get an imaginary number and then you rotate your handset 90 degrees. What kind of number do you get then? Right? All right, so with this framework in mind, we're in a good position to discuss and look at trying to derive Euler's theorem. And Euler's theorem is really just a way to relate a complex number and write it down in a different format. So to get to it, let's first go ahead and look at the expressions x and y, right? So you can see that this distance x, isn't this just hypotenuse times cosine of the angle? Right? And what was this hypotenuse? What was the length of that, right? That's magnitude of z. So I can basically write x is the magnitude of z times cosine of the angle, which is theta in this case. Similarly, y is just magnitude of the vector z, or the hypotenuse, times sine of the angle theta. Right? I think everyone agrees with that. Let's plug this back into this expression down here. So we see that, okay, z, an alternative way to write this is, okay, it's magnitude z cosine theta plus magnitude of z sine theta, and don't forget the I on the end, right? Okay, now let's go ahead, and if you remember, what is cosine and sine? Cosine of theta, it's actually the definition of cosine, it's an infinite series. Cosine is just an easy way, or this COS is an easy way that we don't have to keep rewriting this infinite series. So the infinite series for cosine is actually the sum from n equals 0 to infinity of this odd quantity. It's minus 1 to the n times theta to the 2n all over 2n factorial. Right? Okay, so what this looks like is, let's write this out for a couple of terms. So the I equals 0 term is just a 1, right? Because this is 0. Yeah, this comes out to just be a 1. Now, the I equals 2 term, it's, sorry. This is the, maybe I should write it in another color. This is the n equals 0 term, right? Okay, so now let's look at the n equals 1 term. So again, just jam in n equals 1 everywhere. So you see this is going to work out to, at the end of the day, when you work all that out, this is going to be theta squared all over 2 factorial. Okay, and then let's look at the n equals 3 term. Okay, this thing here is going to flip the sign, S-I-G-N of it, so you get a minus, oh no, I'm sorry, I already screwed the signs up. This should be minus, and then we get a plus. There we go. Okay, so this will be theta to the 4th all over 4 factorial. And I think you get the pattern. This is just going to keep going. So then you're going to get theta to the 6 factorial, right? This one right over here is the n equals 4 term. Oh, I'm sorry, I'm already off by 1. Whoops, okay, sorry, 2, 3. There we go. Sorry, that's a little bit more consistent. But anyway, this is what that infinite series is going to look like, okay? Now, sine is also something similar. So sine of theta is shorthand notation for a very similar infinite series. So that's n equals 0 to infinity of, it looks very, very similar. So this is, again, minus 1 to the n, and it's theta now to the 2n plus 1 all over 2n plus 1 factorial. So again, let's look at the n equals 0 term. In that case, you actually end up with just theta. Okay, and then you get minus theta cubed over 3 factorial for the n equals 1, and then you get plus theta to the 5th over 5 factorial, and then you get minus theta to the 7th over 7 factorial. And I guess I should have wrote dot 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 on these, because right, these just keep going on and on and on, right? Okay, so now, tell you what, let's take these expressions, cosine and sine, and let's examine an odd quantity. Let's see, where do I want to do this? Tell you what, let's go ahead and erase this picture. We can easily redraw this if we need to. Okay, but let's keep these two things in mind, and then let's go ahead and investigate what does the term cosine theta plus sine theta I look like. Okay, namely this thing, right? You can kind of see cosine theta and sine theta I. Okay, so let's write this out. So cosine theta plus sine theta I is equal to, and maybe let's do it like this because I want as much space as possible. Okay, so cosine theta, it's just this infinite series. So let's write down a couple of these terms. We don't need to write all of them out. So this is going to be 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus yada yada yada, right? This whole infinite series, right? This thing plus, okay, sine theta is, again, this entire infinite series. So again, let's just write down a couple of these terms. We don't need to do all of them. So it's theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial plus da 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 da. And then again, don't forget the I, right? So this is I. Okay? Okay, so now let's distribute this I through these terms, okay? So again, this is the same, so let's just do that. Plus, okay, in this case, we end up with theta I minus theta cubed over 3 factorial I, right? Plus theta to the 5th over 5 factorial I plus yada yada yada, right? Okay, now let's go ahead and make the note that, you know what? I squared is -1, right? And furthermore, I cubed, right, is just minus I. And I to the 4th is +1, right? So long story short, you can rewrite this entire term here in parentheses as, let's write this out. We'll do one more step here. Okay, so this, again, still the same. I want to examine this and rewrite that one, okay? So you can actually write this thing as theta I plus, oh no, sorry, excuse me, I want to rewrite all of them. Tell you what, let's do this first, and then, sorry, we are going to mess with this. Okay, this is theta I over 1 factorial, right? That's this term. The 1 factorial didn't do anything. Plus theta cubed I cubed over 3 factorial plus theta to the 5th I to the 5th over 5 factorial plus yada 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 all the way down the row, okay? And then over here I do want to mess with this because I want to do it in a similar fashion. So this here, that can still stay a 1, right? But now I could actually rewrite this here as plus this term, right? This could now be plus theta squared I squared all over 2 factorial plus theta to the 4th I to the 4th all over 4 factorial plus yada yada yada, right? Does that make sense? So that's interesting. This is almost all of the even powers. This is all of the odd powers. But now, you know what? Let's combine them. So if you look at this thing long enough, can be rewritten as 1 plus theta I over 1 factorial plus theta squared I squared over 2 factorial plus theta cubed I cubed over 3 factorial, right? So we're just pulling alternating terms, right? Plus theta to the 4th I to the 4th over 4 factorial plus theta to the 5th over I to the 5th over 5 factorial plus yada, 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 etc., etc. So by now you see the pattern, right? This whole thing can be rewritten as summation from n equals 0 to infinity of the quantity theta I to the n all over n factorial, right? And this should look really similar. This is a very, very famous infinite series. This is the same thing as e to the I theta, right? Or whatever this thing is inside the power, right? So again, what we end up with is at the end of the day, this weird combination of cosine theta plus sine theta I, it's the same thing as e to the I theta. So maybe we should write that down. Let's go ahead and write this down maybe and box it up because that's pretty important. Plus sine theta I, right? This is e to the I theta. That's the same thing. Okay, so finally, let's go ahead and substitute that into this expression for z, right? So just plug this in here, okay? So long story short, tell you what, I hate to do this and make this messy, but we're really, really darn close. You could rewrite this, right? If I factor out the magnitude of z out in the front, you would just be ending up with cosine theta plus sine theta I, which we said was e to the I theta. So here's e to the I theta. Right? So here is an alternative way. This is the complex number z. So here's another way to go about representing a complex number. So you could either have it in quote-unquote rectangular format, right? Z is x plus y times I, right? This is sort of quote-unquote rectangular, right? And this is almost like a polar representation, right? It's, again, if you draw the picture of the real imaginary axis here, and you have the z hanging out here, right? This is almost saying here's the magnitude of z, and here's the angle theta that's associated with it, right? So all that information is embedded in this representation of that same complex number, right? So this is sometimes referred to as Euler's theorem or Euler's formula. And it's just another way to represent a complex number. And we're going to see later on that sometimes it's more convenient to deal with complex numbers here in rectangular format. Sometimes it's easier to deal with them here using Euler's theorem and Euler's formula. Okay, so okay, let's see. I think that's probably a good way to take a moment to pause, and I'll erase the board and we'll take a look at another aspect of this. All right, so before moving on, I wanted to introduce another relevant concept. So to do that, let's go ahead and quickly draw our picture where you've got our real imaginary axis, and we've been visualizing the complex number z is x plus yi, something like this, and then we are looking at it as also a vector which had component x, y, and then this angle theta, right? Where we had now shown that using Euler's theorem, you could write this in sort of polar format, right? We could say this is a complex number z is a magnitude of z, right, times e to the I theta, right? Sometimes you'll also see this written as z is, you know, a magnitude of z and then multiplied by, say, like the angle of z. All this is basically saying is, again, that this vector is basically a magnitude and an angle. So the angle of z is basically theta, right? So that's kind of the other way that you might see this written. Now, while we've got this picture up, another interesting concept that we might want to investigate is the idea of a complex conjugate. And a complex conjugate of z is actually very simple. It's basically this vector z reflected over the real axis. So now it would look something like, let me draw it in another color, maybe green. So here is the complex conjugate of z. Let's denote that as z bar. So again, this is a little bit confusing because we have been talking about z as a vector, and I know a lot of times in notation wise you'll see a bar on top of a letter to denote a vector, but really in this context of complex numbers we want to use this bar to denote a complex conjugate. So this is the vector z bar, or the complex conjugate of z. So you can easily see that z bar, it's got the same real component, but the imaginary component is now negative. So it's something like this, right? So here's how to write the complex conjugate, or the conjugate of z, right? This is in our rectangular format, right? But using our previous discussion on Euler's formula, the alternative way we could write this, right, is that z is a magnitude of z bar times an angle associated with this vector z bar, okay? And again, we see the magnitude is actually the same magnitude as z, right? So you could also write that this is just same as magnitude of z. And now the angle associated with z bar, well, that's this angle right here. Let's call this angle, I don't know, phi. Something like that, right? So you could say this is e to the I phi. But now, again, take a look at what's the relationship between phi and theta. They're just negative of one another, right? So another way you could write this is magnitude of z e to the minus I theta, right? So again, keep this in mind. This here is z bar, an alternative expression for z bar, right? And again, this is now the conjugate of z in quote unquote polar or Euler or however format you want to look at it. So again, keep in mind, take a look at it. The z bar and z, the only difference, right, is the angle, and they're just negatives of one another. Okay, so let's file that little fact away because we're going to use this again in just a second. All right, so let's start talking about a little bit of complex algebra. And this doesn't mean difficult algebra, it just means algebra using complex numbers. So to do this, let's consider two complex numbers, a z, which is an x plus yi. And again, we could write this in Euler format or polar format if we want. We can call this a magnitude of e times, let's call this like an angle of z of say theta. So in other words, you could say magnitude of z e to the I theta, right? So here's z. So again, the picture that might go, well, I'll tell you what, let's draw the picture after we define the other one. So the other complex number let's consider is w. This has real component u and imaginary component v. And again, you could write this as magnitude w times angle. And this here, this angle can be something different, phi. And again, there's no relationship between theta and phi in this case. So we're going to have to write this something like this, right? So again, the picture that goes along with this is that we have our complex plane, and now z could be anywhere. Let's put z here, right? Here's z, and here's angle of z, which we're calling theta, right? And then let's pick some other complex number, w, I don't know, over here. Here's w. And then here's this angle phi, which is associated with it. And obviously the magnitudes are the lengths of these guys. Okay, so now given these two numbers, they don't necessarily have any relationship to each other. Well, let's talk about some complex algebra. So to start things off easily, let's just talk about equality, right? So equality is pretty easy, right? Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal, right? So let's just write that down. So two numbers, in this case, we said z and w are equal, basically if and only if the real parts and complex parts are equal. So in other words, you need, so for z to equal w, this happens, right, if and only if x is equal to u, and I'll use kind of a Matlab operator, right, the double ampersand, and if y is equal to v. So again, this is a little bit of a duh moment here, right, but I thought it might just be good to just state that fact, okay? So let's keep on going. Let's do a little bit more abstract things. So how about addition, subtraction? Again, this is not mind-blowing at all. It's basically like vector addition, subtraction, right? So if you have two numbers, right, this z and w, and you want to add the two together, well, all you got to do is just add the real components. So you get x plus u, and then you add the imaginary components, w plus v, and then times I. Okay? So that's what we pretty much end up with, and nothing fancy there. So you know what? Subtraction is just the same. So z minus w, it's basically you subtract the real components. That should be a u. My handwriting, apologize for that. And then a y minus vi, right? So addition and subtraction is nothing to worry about. How about multiplication? Okay, let's look at multiplication. Multiplication, again, let's take our z times w. And now what we can do is let's just write it out. So z is x plus yi, and then multiplied by w, which was u plus vi. Right? Okay, so now let's just FOIL this thing out. So this thing is now xu plus xvi plus yui plus yvi squared. Okay? So now you got to go ahead and recall that, all right, I squared is just -1. Right? That's the idea with a complex number. So this becomes a -1. Let's group these terms. So we end up with xu, and I'm going to actually move this over here. So this is going to be minus yv, right? That's this and this term, right? Plus now xv plus yui. Okay? So in other words, here's your new real component, and here's your new imaginary component of your number. So here in multiplication, you can just go ahead and brute force this using foiling out the expression. Now, alternatively, you could also use Euler's formula to make this a little bit easier. How about let's use Euler? So again, let's do the same operation, z times w, okay? But now let's do this in Euler's format. So in Euler's format, z was what? Z is magnitude of z times e to the I theta, right? Okay, w is magnitude of w times e to the I phi, right? So this whole thing is just magnitude of z times magnitude of w times e to the I theta times e to the I phi. If you remember the rule for these, this is now just going to become e to the theta plus phi I. Okay, so this is a little bit easier way to go about this. So you see that multiplication of complex numbers, you just multiply their magnitudes and then you linearly add their angles together, right? So that's another easier way to maybe look at it as opposed to brute forcing it out. Both of them should get you the exact same formula. Now, this is a little bit interesting because now this gives a little bit of insight into why that discussion we had earlier about complex conjugates are interesting. So maybe let's do this up here. I think we have enough room. What happens if you look at z times z bar, right? You're looking at multiplying a number by its complex conjugate, right? Well, again, let's use Euler's formula here. So this is magnitude of z times times magnitude of z bar times e to the I theta plus phi, right? And now we know for a complex conjugate, phi is just negative theta. So this actually goes away, okay? So what do we end up with? We end up with e to the 0. So actually, we end up with just magnitude of z times, and we remember that magnitude of z bar is the same thing as magnitude of z. So it's actually just this, right? So this is actually really fascinating, that when you multiply a number by its complex conjugate, what ends up happening? You actually end up with just a real number, right? And you end up with, so maybe let's write that down. So multiplying a complex number by its conjugate yields a real number. So you lose all complex parts, right? So this is actually pretty darn useful, all right? Okay, so let's use this fact to do division. So actually tell you what, give me a second to erase the board and let's keep going on our list and we'll look at division. All right, so let's go ahead and look at how about division. Okay, so again, what I'd like to do is I'd like to divide these two numbers, z and w, by one another. Okay, so let's just write this out. So again, z is x plus yi divided by u plus vi. Okay, so now let's use the rule we just acquired and basically multiply the top and bottom by the complex conjugate of the denominator. Okay, so we're going to multiply by u minus vi and u minus vi. Okay, so what we know is that down here in the denominator, we're going to end up with a purely real number. So let me just maybe write it like this, is maybe the easier way to do this. So you can easily see that, okay, you go and use the exact same rule we did earlier. We FOIL this thing out. We FOIL this out. Again, you make sure you take into account that there's a negative sign here. So this is a little bit boring algebra. I'll save you the details of me working this out. And why don't you take my word that when you do this, you're going to end up with... you'll end up with this thing. You'll end up with xu plus yv plus yu minus xvi all over u squared plus v squared. Okay, so here's the real part, and here's the imaginary part. Actually, to make that even more obvious, let's just go ahead and write this out. I'll distribute this to this side and this to this side. In other words, I want to isolate the real part, so it's xu plus yv all over u squared plus v squared, and then plus the imaginary component, which is yu minus xv all over u squared plus v squared times I. There you go. So here is what z over w looks like. Again, now you end up with another complex number. Okay? Okay, cool. Let's keep on rolling. How about powers and roots? Okay, so in other words, what about you want to look at z to the n? So you want to take this complex number and raise it to the nth power. Okay, so if you think about this, this is really just z times da 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 times z, and you're going to do this n times, right? So it's really just spamming the multiplication rule n times. And the easiest way to look at this, I feel, is probably to write out all these z's using Euler's formula and using that rule. So let's do it one at a time here. So this is magnitude of z times e to the I theta, right? That's the first term, times magnitude of z times e to the I theta, right? That's the second term, times dot 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 all the way down to magnitude of z times e to the I theta, right? So you see the pattern. Basically, these magnitudes are going to multiply, so you're going to end up with magnitude of z to the n, right? And then the angles are just going to linearly add n times, right? So you're going to have e to the n theta I, right? So here you go. Here's z to the n. This is actually not that bad, right? So that's actually pretty easy. How about roots? So you wanted to take the z to the 1 over n, the nth root of the complex number z. Well, this is really just a power, except the power, instead of being a positive integer, it's a fraction. So it's basically the exact same thing, right? You're going to end up with that exact same result. You're going to end up with magnitude of z to the 1 over n, right, times e to the theta over n times I, right? Yeah, so that's basically all we're going to end up with. Okay, so there you go. So that's how to do powers and roots. Okay, so yeah, I think that's where we're at. Tell you what, just to make sure we're all on the same page, give me a second to erase the board, and let's apply all of these rules with actual numbers in a concrete numerical example. All right, so let's go over just a very simple numerical example. So in this case, let's go ahead and pick some z value of, how about 3 minus 2i and a w of minus 4 plus I, okay? So I think it might behoove us to just draw out what these look like so we can get a reasonable idea of these. So, okay, so z is over here, let's make 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so z here is at positive 3, negative 2i. So here's z, okay? So there we go. Here is, whoops, that's a horrible vector. I'll draw it like that here. Okay, so here's z, and then here is the angle of z. I guess let's draw it like this. So here's what we were calling theta earlier, okay? And then let's draw w here. W is 1, 2, 3, 4, negative 4 plus 1. Okay, so it's actually up here. So here's w. And again, we could draw it as a vector. and here is its angle associated with it, which we were calling phi earlier. Okay? All right, so let's go ahead and do a couple of operations. For how about part A of the example will be, let's just go ahead and calculate something really simple, z bar. And then from part B, let's go ahead and calculate z plus w. And then for part C, let's go ahead and calculate z times z bar. And then for part D, let's go ahead and calculate z to the fifth. Okay? All right, so just for giggles, let's go ahead and get started. So for part A, where we're just looking for z bar, that's really simple, right? So z bar, it just has the same real component, but it has the opposite sign of the imaginary component. So here you go, 2i. So again, let me just draw that maybe in blue so we can see what this thing looks like. So here is z bar. Okay, so there it is. It's just reflected over the real axis. Okay, so that's great. That's super easy. Okay, how about let's moving on. Part B, I want to look at z plus w. Okay, so again, if you just write that out, you end up with z is what? It's 3 minus 2i plus w, which was negative 4 plus I. So again, just add the real components. So I think we get negative 1, and then you end up with what? Negative 1 times I. Right? So here's z plus w. So nothing super fancy. I don't know if it's worth it drawing it. I think you get the point at this stage of the game of what this thing looks like. Okay, let's go ahead and do part C. Okay, so this is looking at z times z bar. Okay, so we're going to multiply the value z by its complex conjugate. Okay, so we could do this using either of the formulas we ended up with earlier. But for practice, you know, maybe it might be helpful to use, let's see, which one are we going to use here? I can't remember what I ended up doing in the example. Oh, okay, yeah, let's use Euler's formula. So Euler's formula said that, okay, when you multiply these two things together, this is actually just, what do we end up with? The magnitude of z squared. Okay, so let's get a couple of these items first. So sidebar, maybe what we should, it might be helpful now to calculate things like magnitude of z. Okay, so magnitude of z, it's just the length of that vector z. So this is just square root of the real part, which was 3 squared, right? Minus the imaginary part squared. Plus negative 2 squared, right? So magnitude of z in this case ends up to be 9, 4, 13, root 13, right? Okay, and now here, let's get theta. Right? Theta here was the same thing as angle of z, right? The other way to think about this. So again, we see the picture there. So what we're going to do is, here's the place where we got to be a little careful, right? You either do this in Matlab with a 4-quadrant A tan 2 of you give it the y component or the imaginary component first, right? So in this case, it would be negative 2, and then you give it the real component 3, right? This is the same thing as if you had gone over to Mathematica, right, and you called arc tan, but you have to give it in Mathematica the real component first, and then the imaginary, right? So again, got to be a little careful which software package you're using and how to call it. Both of these results, by the time you convert this thing to degrees, you think you end up with about negative 33.7 degrees, which makes sense, right? If you look at this picture, right, this angle, it could either be a positive 200 some odd degrees or negative 33 looks about right. Okay, so great. Those are the two sidebars. So at this point, I think we can easily calculate magnitude of z squared. Here's magnitude of z is root 13, so its squared is just going to be 13. So there you go. Here is z times its complex conjugate is just the number 13. Okay, let's go ahead and do the last one just to make sure we're all on the same page. So part D was trying to calculate z to the fifth. Right? Okay, so we said z to the fifth, right? Using our power rule earlier that we developed, this is just magnitude of z to the fifth times e to the 5 theta I, right? Okay, so magnitude of z was root 13, right? Now I got to raise this to the fifth, and then e to the, oh gosh, I guess I should have computed what this was in radians. Shoot, did I have that? Dang it, I didn't have that in radians. Okay, tell you what, I guess we can kind of fake this. Here, we know that it is negative 33.7 degrees, but then I'm going to convert this to radians, so this is going to be pi over 180. There we go. There we go, times I. Right? So there you go. This is what we end up with. So by the time you crunch all these numbers, what is this? This is going to be 609.3-ish. And then I think this whole thing up here comes out to be about e to the negative 2.94i. Okay, so here you go. This is z to the fifth. So z to the fifth, again, if you wanted to plot this, the magnitude is 609.3. So it actually, it's shooting way off. And the angle is that's about that's about pi, right? So pi would be 3.14. So let me think about this. So that angle is like not quite there. So it's somewhere, it's probably something like along this line, right? So here is the angle of minus 2.94 radians, right? So okay, here's this vector z to the fifth, right? If its length was 609.3, so it's really going off there, okay? All right, yeah, there we go. I think that's great. So this is a pretty good discussion on complex numbers. Why don't we shift gears a little bit and talk about complex variables and complex functions. All right, so now let's talk about complex variables. And this is actually a real short discussion because it's a simple concept now that we've covered complex numbers. Right? So the idea with a complex number was we were just considering some point z in the complex plane, right? And we visualize it as a vector. Now, all we're going to say is instead of looking at a complex number v, which is static, let's assume that it could change, right? That's all a complex variable is. It's just a complex number who can vary, right? So to denote that, our typical notation is going to be s for a complex variable. So again, this complex variable is going to have a real part, which could be changing. So instead of calling it just a static x, let's call it maybe like a sigma plus omega I, right? So all this is, here is your complex variable, right? And the picture is almost the exact same thing as we drew earlier. S could be anywhere in this real imaginary plane, but it just has component sigma and omega for real and imaginary respectively, but this thing could be varying all over the plane. We could be looking at different values of s, so it's not just a static complex number. So complex number, complex variable, very similar to being the same thing here. It's just one varies and one doesn't. So let's extend this idea now. How about complex functions? Right? And again, this isn't really that complicated. It's just this adjective of complex in front of the word function. What does a function do? Right? So if you have some function, let's call this thing f. Right? In a normal, real situation, all a function is it's something where you give it some inputs, it does something to the inputs, and it spits out some outputs. Okay? That's all it is. So if you want to add the word complex to this thing, all you're saying is that the inputs are possibly complex variables. Right? And the outputs are possibly complex variables. Or numbers, however you want to think about it, right? So that's all a complex function is. So again, maybe we'll denote this as f, and the input is going to be now a complex variable s, okay? And this thing could still have a real component. It could have a real component to the function. So maybe let's call it like I don't know, an fx or something plus an fyi. Right? So all it's saying is that you stick in a complex variable s, it's going to do something and produce a real part, and it's going to do something else and produce an imaginary part. That's all this thing is. Okay? So the most common type of complex function that we are going to be considering in this class, or actually in this discussion of ordinary differential equations, is something that looks like this. Maybe let's write this down. So for ordinary, f of s will typically have the form, let's write this out. So this is going to usually look like f of s. It's going to be a ratio of polynomials. So basically we're going to have a ratio here. In the numerator, you're going to have basically a polynomial of order m, and I'm going to write it like this: s plus z1, s plus z2, yada, 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 all the way s plus zm. Okay, and then you're going to have another polynomial in the denominator of order n. So you're going to have s plus p1, s plus p2, yada, 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 all the way up to s plus pn. Okay, and you might have a gain k here. Okay, this is typically referred to as a function in zero-pole gain, or ZPK. So I'm going to write this down, zero-pole gain, or ZPK format, because what these z's are in the numerator, these are referred to as the zeros. So here, let me just write this out. Negative z1, negative z2, all the way up to negative zm are called the zeros of the function. And negative p1, negative p2, all the way out to negative pn are referred to as the poles of the system. And this arbitrary k here is just a static gain. So most of the complex functions we consider when dealing with ordinary differential equations are going to look like this. Now, you can almost tell why these get their name, right? Why are these values of negative z1, negative z2, negative zm, why are those special? Well, if you look at this, when the complex variable s takes on a value of negative z1, what happens? This term in the numerator becomes 0. Therefore, the entire complex function becomes 0. Right? So what this means is when s takes any of these negative z values, the function goes to 0. So again, maybe if we were to draw this here, like here's a location of minus z1, minus z2, whatever, right? All the way at minus zm. At any of these locations, the function is 0. Right? And f of s equals 0 at those locations, right? Contrast that with right here. What happens if this complex variable s took on any of these values? Negative p1, if it took on negative p1, this term right here would be 0, and you would have a divide by 0 error, or well, not error, but you'd have a divide by 0. What does this function look like? What does it come out to? It's not 0, it's infinite, right? So kind of coming out of the board, you can kind of think of as this thing is infinity. So here at negative p1, f of s is actually equal to, infinity, plus or minus, depending on this. So it's like a pole that comes sticking out of the board, right? At this value, the function is doing whatever, but then when it gets to this location, it goes, wha-bam, it comes out and it is sticking up like a pole. And it's the same for any of these p values, at negative p1, negative p2, all the way up to negative pn, any of those, the function is going to blow up effectively, and you have this pole effect. Okay, so let's just take a quick example. I just want to make sure we're all on the same page of this, so we can kind of classify this, because this is going to be key in a little bit. So let's look at some function. Let's call it g of s. How about instead of just using f? F, g, it can be any notation. It's just a complex function. So let's call this thing. How about k s plus 2 s plus 10 all over s plus 1, s plus 5, and then s plus 15 squared. Okay? All right, so if we wanted to classify this in terms of zeros and poles, we would notice that there's a, let's call it a simple zeros, at s is equal to what? Negative 2, right? And s is equal to negative 10. Okay? And there are simple poles at s is equal to 0, right here. S is equal to minus 1 and minus 5, okay? And now there are two repeated poles at s is equal to minus 15 and also at minus 15, right? Because right here, there's two values, right, that will basically give you two poles, or there's two roots to this polynomial if you want to think about it. They just happen to be at exactly the same location. So this multiplicity is going to come into effect a little bit later. Okay, so with that being said, I think this is a good spot to leave, because we've now covered a reasonable amount of discussion for complex numbers, complex variables, and complex functions. So I want to leave this here because this would be the end of the abstract mathematical discussion. I hope you're going to join us at our next lecture where we're going to leverage this information and talk about applying this to the Laplace transform, which we're going to see later on down the road has real good effects, and it's a really good viable way of solving ordinary differential equations. So with that being said, if you like the video, please consider subscribing and hitting that like button because it really does help me continue making these videos. And with that being said, I really hope we'll see you at our next discussion because things are really starting about to heat up. So until then, I hope to talk to you later. Bye.